Dear students, welcome back to Chem Aspire. In this lecture class, we are going to discuss about the d orbital splitting in octahedral complexes. So we know the formula for octahedral complexes M, L6, N plus. So this is the general representation of a octahedral complex where N is the metal cation and L is the ligand. So in this octahedral complex, you have a central metal cation and there are 6 ligands, and these 6 ligands are oriented towards the 6 corners of the octahedron. So let us draw the structural representation of the octahedral complex. And we have 6 ligands at the 6 corners of the regular octahedron. So we are also representing the axis as x, y, and this is your z axis, right? So this is the structural representation of a octahedral complex, and we know that the d orbital, we have a metal cation and there are 5 d orbitals in the metal cation, and these 5 d orbitals are degenerate in nature. We know what are the 5 d orbitals we have in the metal. They are dx square minus y square, dz square, dx square minus y square, dz square, dxy, dyz and dxz. So these are the 5d orbitals, and all these 5d orbitals are degenerate. That means all of them are having the same energy. According to crystal field theory, we know that the energy of all the 5d orbitals are same. However, when the ligand approaches, the degeneracy of the 5d orbital is disturbed. That we have seen in the crystal during the salient feature, when we saw the salient features of the crystal field theory, right? Suppose say now you have a metal cation and there are 5d orbitals and there are electrons in the 5d orbitals of the metal cation. Suppose say when the ligands are approaching the central metal cation from the either end of this axis of each of these axes, right? The electrons in the d orbitals of the metal are repelled by the negative point charges. Let me repeat once again. When the ligand approaches towards the central metal cation from each of these axes, from both the sides, right, the electrons in the d orbitals of the metal are repelled by the negative point charges. We have to recall what we have studied under the salient features of crystal field theory, right? We are considering that ligands as point charges, right? The ligands may be a negatively charged ion like F minus, Cl minus or Cn minus, or it can also be a neutral molecule, right? The negatively charged ions are called as the point charges, and we have also discussed that the neutral molecules when the neutral molecule approaches the metal cation, they are polarized by the positive charge of the cation. Therefore, a polarity is created in the molecule, and only the negative part of the neutral molecule will be attracted towards the central metal cation. So with this understanding, we have to come here and see when the ligands approaches the central metal cation, the electrons in the d orbitals of the metal are repelled by the negative point charges, right? Negative point charges. Because of this repulsion causes the energy of these 5d orbitals to rise to a next level, right? Therefore, these 5d orbitals are rise to a next higher energy level. So here again they are all degenerate, dxy, dyz and dxz. Here also it is all degenerate. But this position is called as the hypothetical situation. This is called as the hypothetical situation. What do you mean by hypothetical situation? Because this situation is only a theoretical situation, or it is a hypothetical situation. That means this is possible only when all the ligands are approaching the central metal cation or at the same distance from the d orbitals of the metal. This can happen only when the ligands we are approaching the central metal cation at the same distance. But this is not actually happening. We know that when the ligand approaches, there is a degeneracy is disturbed, and the orbitals are split into two types of orbitals as EG set of orbitals and T2G set of orbitals, right? So this EG orbitals, we know the structure of this EG orbital where the lobes are lying along the axis. In dz square, the lobes are lying along the axis, and x square minus y square, the lobes are lying along the axis. Whereas in the case of T2G set of orbitals, the lobes are lying in between the axis. Because of this variation in the energy in the d orbital, right? Because of this variation, the electrons, the d orbitals, EG set of orbitals are experiencing greater repulsion because the lobes are lying along the axis. They experience greater repulsion when compared to the repulsion that are experienced by the T2G set of orbitals. Right? So what we have seen now, when the ligand approaches the central metal cation, right, there is a repulsion between the electrons in the metal with that of the negative point charge. So this is raising the level of the 5d orbitals to a next higher energy level. So we call this energy level as a hypothetical situation, because this can happen when all the ligands are approaching the central metal cation or at the same distance. Right? But this is not actually happening because we have 5d orbitals. We know the structure of these 5d orbitals. EG orbitals, the lobes are lying along the axis, right? Whereas in the case of T2G set of orbitals, the lobes are lying in between the axis, right? Because of this, the EG orbitals are gaining, since they are along the axis. The EG set of orbitals are experiencing greater repulsion by the ligand, by the point charges, than that are experienced by the T2G set of orbitals. Therefore, here the splitting happens, and EG set of orbitals are raised to a higher energy level. EG set of orbitals are raised to a higher energy level, and T2G set of orbitals are lowered. So here we have dx square minus y square and dz square. So this is the EG set of orbital, and this is here T2G set of orbital. dxz. This is your T2G set of orbital. So here, because of the greater repulsion of the d orbitals by the point charges, EG orbitals are raised to a higher energy level, and T2G orbitals are experiencing lesser repulsion. They are lowered to the energy level is lowered, and the difference in energy level between T2G set and EG set of orbital is called as the crystal field stabilization energy. This energy difference between EG and T2G is called as the crystal field stabilization energy, which is represented by del 0 or the value of dq. This is called as the central crystal field stabilization energy. And there is a situation where there is no splitting of orbitals happen, and this dotted line is called as the barycenter. This is called as the barycenter. Right here, the energy difference between this barycenter and the EG set of orbital is equal to plus 0.6 del 0, or it is 6 dq, and the energy difference between barycenter and T2G set of orbital is equal to minus 0.4 del 0 or minus 4 dq, right? So this is about the splitting pattern in octahedral complexes. So let us recall what we have studied under this heading. So we know the formula for octahedral complex is ML6N+, where N is a metal and we have 6 ligands, and these 6 ligands occupy the 6 corners of a regular octahedron, and in the metal all the 5d orbitals are degenerate. When the ligands approaches the central metal cation, the electrons in the d orbitals of the metal are repelled by the negative point charges of the ligands. Because of this repulsion, the energy of the 5d orbital is raised to a higher energy level, which is a hypothetical situation. But when the ligand approaches, the Eg set of orbitals are experiencing greater repulsion than the T2g set of orbitals. Therefore, the energy level, Eg level is raised to a higher energy level. Eg set of orbitals have higher energy levels and T2g set of orbitals are having a lower energy level. There is a state called as the no splitting state, and it is represented by a dotted line which is called as the barycenter, and above the from barycenter to E to Eg, the energy difference is plus 0.6 del 0, and the energy difference between this barycenter and T2g is minus 0.4 del 0 or minus dq. The energy difference between the Eg and T2g are called as the crystal field stabilization energy. That's it for today. We'll see you in the next class. Thank you.